Good afternoon, and welcome to the 34th anniversary celebration of the Tyler Prize for Environmental Achievement. I'm Linda Duguay, and it's my very great privilege to serve as the executive director of the Tyler Prize here at the University of Southern California. I've held this post for the last 7 years, although the prize has been a part of USC for well over 25 years, and as I say, the prize is over 34 years old. It is my truly great honor to introduce to you this year's truly outstanding 2007 Tyler Laureate, Dr. Gatze Lettinga. He's an emeritus professor from Wageningen University. I've been practicing and keep at it. This Dutch is very difficult, but I'll keep working at it. He's, of course, from the Netherlands, and he's an extremely dedicated engineer, educator, and researcher. And he undertook and brought to the forefront some very important research and engineering technology with regard to reducing contaminated industrial wastewater using anaerobic microbial systems. And as he always gives credit to his colleagues at Wageningen University and the people that he's worked with, he developed something called the upflow anaerobic sludge bed reactor system. And this system stands behind about 3/4 of the world's anaerobic systems for treating industrial and residential wastewater. I think his work has revolutionized wastewater treatment, valorization, and he's kept it affordable. The benefits of his reactor system include major savings in energy, cleanup of recalcitrant, even toxic effluents, and efficient biomass energy conversion. So it's, as I say, time for Gatze to tell us about his views on environmental sustainability. He'll talk for a while. He's got a wonderful PowerPoint presentation, and then he'll take a few questions, and then hopefully you will all join us across the quadrangle back near Founders Park. We'll lead you over there with Gatze and the League to our Tyler Prize Pavilion, where you'll actually be able to see photos and the credits for all the different laureates that have gone before. So please join us for a nice reception.
Thank you, Linda. Ladies and gentlemen, it is a very big pleasure for me to be here. And in my presentation, I want to give an overview of the work we did in Wageningen. I want to explain you what are the prospects to come to a better and sustainable environmental protection in this world. And I go step by step through the field. And this is a picture of beautiful Amsterdam. I want to make some advertisement for Amsterdam. It is a very beautiful city. The title of my presentation is Degradation to Build Environmental Sustainability. Degradation is fragmentation, but it's not destruction. It is a smooth microbial breakdown of all kinds of organic materials. And we can use this to create an environmental sustainability. A clean, secure, and harmonious life environment for everybody. Everybody in this world. That is what we should try to achieve. And I think we have all the tools. We have all the knowledge, and it is just a matter to use it in the proper way. So what do we want in protecting the environment? We want resource conservation. Wastes are resources. We want to conserve the nature, biodiversity. Pollution problem prevention. No problem creation, prevention. A high degree of self-sufficiency, wherever, not merely in the field of environmental protection, but in any field. Robustness, so no vulnerability, but robust systems. With respect to what is more general, to the society, we need good education for everybody. We need spiritual development of the people and social security. I will come back to that. So how to illustrate that there are reasons for optimisms? In fact, I wanted to start my talk with saying that I want to make a positive, optimistic presentation. Of course, I don't want to give the impression that I am not pessimistic from time to time. So I will mention some of these things. So coming to our field, organic waste, whatever. Dead organic waste, dead organic matter. Various types of biomass. I come back to that later on. Organic pollutants in wastewater. We need valorization. It are not waste, it are resources. And I am going to explain now how we could achieve this. It is a completely natural sequence of processes, biological processes completed, if necessary, with physical chemical. So we have these types of biomass. The first process we need to apply is anaerobic degradation. Conventional anaerobic digestion processes or high rate anaerobic wastewater treatment processes. It can be also sulfate reduction. If we have anaerobic digestion or rotting somewhere in nature, we smell it because of these H2S or other volatile sulfur compounds. So everybody is warned. Something is happening there. But what we want is to use this process in the proper way. Then we generate from biodegradable organic matter methane. Of course, it's a resource. It is an energy resource. CO2, some H2S, and possibly hydrogen, just by manipulating the system. But very important, we also produce soil conditioners. Anaerobic treatment is the first step for removing biodegradable organic pollutants from a waste or a wastewater. I don't support, maybe we can have discussion about that, the use of lagoons or wetlands. I don't support it because they are very extensive treatment systems, and in fact we don't recover the energy produced from the digestion processes taking place in these systems. The same, I don't like landfilling. It is old-fashioned. For the same reasons. And also not composting. Because composting, we convert biodegradable organic matter and heat. But low-calorie heat, so of little value. So this is the heart of the system. But it is not a complete treatment. The effluent of the anaerobic treatment system contains the nutrients. Ammonia, phosphate, volatile sulfur compounds, salts. So we cannot discharge the effluent of an anaerobic reactor into a surface water. We could use the effluent for irrigation and fertilization. So that is the first step to a further valorization. But the point is, I'm going to emphasize several times, the point is, the more concentrated we keep our waste, the less diluted, the more concentrated is the effluent with respect to ammonia, phosphate, and these kind of very valuable fertilizers. The next step, we removed already all biodegradable organic matter in the first step. So what is left is just found in the soil conditioner. The next step is microaerobic step. Just putting in aeration, a little bit aeration, in order to get rid of malodorous compounds, H2S. And we saw this many, many years ago in the first anaerobic reactor, a kind of a white precipitate at the surface, liquid gas surface interface of the reactor. and it turned out to be sulfur. And later on, we started doing research in order to find out what is happening. It's a biological microaerobic conversion process, extremely interesting. Next step is physical chemical treatment in order to recover in a concentrated, very concentrated form, the ammonium phosphate. And the last step, so we don't refuse to use any of the conventional processes, is an aerobic polishing step. Then we have a fine effluent, an extremely well-treated effluent at a very low cost. This is the natural biological mineralization sequence principle, NBMS. I hope you took it, because I'm going to speak about it again and again. So, clearance anaerobic degradation process should be the first biological treatment steps in a sustainable environmental technology, and not aerobic. For stabilizing the biodegradable organic matter, I just summarize. For generating energy carriers, methane, possibly the oil companies are very interested in that, and hydrogen. It's a little bit complicated. Making available the nutrients, not removing. So we need an additional step. Producing soil, organic soil conditioners. This microaerobic first post-treatment step is extremely promising. It is the conversion of H to S, but also other volatile sulfur compounds into elementary sulfur, which can be easily separated from the liquid. It is applicable for the removal of H2S from natural gas. It is already applied for this purpose, for this objective. A Dutch company, Parks, is working in this field very much. Shell, oil companies, the big Shell, they are interested in it. But it's also for the removal of malodorous compounds, these stinking compounds. It is microbiology, and I am a technologist. I didn't explain you, but you already understood it, I think. I was educated in Wageningen in physical chemical treatment, radioactive wastewater, but started working in 1970 based on a paper I will mention a few minutes later. And this is, you see, these organisms. This organism is excreting elementary sulfur. And we did this work in very close cooperation with Gijs Kuenen, Professor Gijs Kuenen from the Technical University Delft. He was here for 2 months. Very good cooperation. We did the technology, he did the microbiology. So, supplementary conditions to be met for realizing waste valorization. It is not merely using this NBMS principle of treatment, but we need more. It is extremely essential. We need proper collection systems and transport systems for the residues. In fact, what we need, keep these waste and wastewaters as concentrated as possible. Don't waste any clean water. Use complementary physical chemical treatment methods in order to refine the recovered byproducts. And application, of course, you can recover what you want, but if you don't use them, so this makes a little sense. So we have to use these recovered byproducts nearby the location, somewhere, for agricultural purposes. Here, this is a kind of sustainable environmental protection, directed to pollution prevention, to a high degree of self-sufficiency and robustness, and waste valorization. Then we have a lot of tools in order to realize this. I don't want to go in detail, because it is a general lecture, but just one thing. We should focus on transport limitation. not all these huge transport systems. I come back to that. And focus on sustainable innovations. And with sustainable innovations, I mean innovations which serve all people. So I think with this sustainable environmental protection, we also make a step towards a more sustainable future for our human society. It will help us eliminating the waste of mineral and natural and human resources. It's negative. What I'm saying now is negative. I don't want to speak about negative things, but it's just we live in this world, so I have to mention some. So sustainable environmental protection will help us to eliminate wasting of mineral, natural and human resources. Monopolization of knowledge and technologies. That is what we're doing day by day. Risky, uncontrolled, dangerous robotization. All kinds of powerful, outdated, established groups and institutions. Not so easy. But we have to get rid of it. I don't know how. But maybe anaerobic treatment could help. You are laughing, but I think it is too. So, be realistic again. Is it too optimistic to believe in the realization of a more sustainable society? He is a bit older now. But still he is here. Anaerobic treatment should attain the position in wastewater treatment it truly deserves. That was the first article I read when I came in Wageningen. Knowing nothing about biological treatment. I don't know how and why, but this paper, I took it out of the file a few weeks ago because it was still in Wageningen. I have it now, it is very valuable. So, Perry McCarty, he brought me on the way. And that time, it is the philosopher Teilhard de Chardin. I read his book and I tried to understand it. I understood something. I made more or less my own philosophy from his ideas. But anyhow, he said, a truth even seen by only one person will irrevocably find its way. I just looked to Perry. So what did he do? In 1970, he helped me, because of that article, to find a perfect niche for my academic career, but much more than my academic career. It is more or less my life. Because why? 1970. In 1970, in Holland, we got a new legislation. Everybody who is polluting has to pay the bill. So private industries became extremely interested in finding cheap solutions for wastewater treatment. We expected a great interest for cheap and sustainable systems in the public sector. Expected, but were a little bit disappointed. And we considered anaerobic treatment, it is not considered, but we still consider anaerobic treatment as the proper solution for developing countries, but not merely developing countries, for all countries. So I am going to speak about this anaerobic wastewater treatment system, because most of you are not familiar with it. Only 3 main conditions have to be met. This is so simple. We have to retain a high amount of viable anaerobic sludge. The more, the better. But under high loading conditions with respect to hydraulics and organic loading rate. We need to accomplish a good contact between wastewater and viable sludge. Because if you have no contact, so it doesn't make any sense. And efficient separation of the biogas in the top of the reactor. So here is the UASB system. In the lower part, we have the introduction of the feed, the wastewater to be treated. We have the anaerobic sludge. And this anaerobic sludge has a very high settleability. So we can apply high upflow velocities. The gas is separated here in gas collectors, and the effluent is leaving the system at the top of the reactor. So not any mechanical device. The great advantage here of anaerobic treatment compared to aerobic wastewater treatment, it is resource producing, not demanding. We don't need any electricity. No excess sludge problems, because these anaerobic organisms, they grow very slowly. And the sludge we are creating in this reactor is extremely thick, so the volume is very small. It is simple, cheap, and robust. Can handle very high organic loading rates, up to 10, 15 times as high as conventional aerobic treatment systems. No external power supply, already mentioned. And very important, viable anaerobic sludge, cultivated at some time of the year, can be stored unfed for 6 months, 10 months. And when you have a new feed, new campaign industry, you start simply feeding again. Drawbacks. You always have to speak about drawbacks. I have problems with that, speaking about anaerobic treatment, because I don't see any drawback. So they speak about slow startup. This is just true the first time. But once you started your system, you harvest the sludge, you conserve the sludge, you store the sludge, and you can reuse it for new reactors. So no problem anymore. Nuisance, other nuisance? No, because we have this microaerobic post-treatment. Susceptible? All organisms are susceptible. Aerobic, anaerobic. But if you do know what you do, so there is no problem. Not a real problem. Little full-scale experience, not anymore, except in the public sector. Public sector, I mean sewage treatment. I come back to that. It is true, anaerobic treatment systems just merely remove the organic pollutants. For me, it is a benefit, provided we meet the condition, keep the wastewaters as concentrated as possible, or in case we can reuse the effluent for irrigation all the year long. Merely applicable at higher temperatures. This was the case. But as a result of all the research which has been made during the last 4 decades, we know the system can be applied at very high temperatures, thermophilic conditions, and very low temperatures, even down to 4 degrees centigrade. Just a little bit history, because all this speaking is a little bit tiring, I think. This is the first 30 cubic meter pilot plant reactor in 1973. The system, the project was subsidized by the Dutch government, by one of the ministries of the Dutch government. This is a pilot plant installed at a sugar beet factory. It was extremely successful. And here the group of people working on it. They're a little bit older. I just want to show the man, the flatter. He was responsible for the environmental treatment systems in the sugar beet factory. Extremely motivated to develop sustainable systems. And for me it was exceptional that he came to us in order to cooperate. This was the first big step towards implementation. Extremely interesting, this UASB process is the formation of a very well settling, very active granular sludge. This is so extremely fascinating for all kinds of disciplines, and so important. So this is such a granular sludge, up to 2-3 millimeters in size, very, very well settling, and extremely active because it is composed of viable consortia of anaerobic organisms. But there are a lot of questions, yeah? And I'm not going to, in detail, just mention a few. What is granulation? Okay, I will say something. Why, how, when does it develop? How does it grow, reproduce? Very interesting. Maybe I say a few words. How can it be manipulated? This is fascinating for scientists. How can we cultivate a granular sludge which we want? And how can it be applied for technologists? Bacterial granules. It are mechanically stable aggregates. Each it's his her own identity, like we here human beings. Yeah, the same species, but very different. It's the same for these granules. And composed of densely packed consortia of smoothly cooperating anaerobic organisms. And these organisms which are present in a specific granular sludge, they just develop based on what was present in the wastewater or what was present in the seed sludge. History. Once again, McCarty, he was the first who observed these granules. I read it in his paper, and I read it again a few weeks ago. It is absolutely, you said it, and you observed them, and we observed them a few years later in the USB reactor. And we started very comprehensive research. We observed it, we were fascinated by it, and so we did for decades research. PhD work of a lot of PhD students in the field are here. I will show them a little bit later. We have many different types of granular sludge, depending on the wastewater we treat. Yeah. Here the pioneers. One is here, Loke, where are you? He was the first who started doing the research in this field. And Jules van Lier, he did it in thermophilic, but they did a lot of work in many other fields in this anaerobic treatment story. These granular particles, they duplicate smoothly in a USB reactor through a mechanism of occasional fragmentation. And the how and the why is interesting, but not point of discussion now. New organisms which we need for a specific type of wastewater, because if we want to treat a very new type of wastewater with xenobiotics, we need new organisms. And they should be incorporated in the structures, in the old structures. And this can only be achieved by gentle crushing the old grains and growing them, allowing them to develop new grains together with these organisms we need. And we can, of course, develop completely new grains based on pure cultures. All these kind of things, a lot still has to be done. So, reasons for optimism to get sustainable environmental protection processes implemented. The industrial sector, since '76, very significant progress. First of all, in the proper collection. Yeah, they kept the wastewaters concentrated and separated. Little of any dilution. Minimizing transport. Not all these huge sewer systems. They implemented this NBMS-based treatment technology. And we have excellent business by the companies, the contractors doing the job. Pax and Biotane. And of course, there is a significant better understanding of the basics and the technology of the system. So since '76, the system is applied for many food industries, but increasingly also for complex industrial effluents, forestry and chemical industries. It has a lot of potentials for application under extreme conditions, high salinity, high temperatures, low temperatures. And many industries are on the way towards closing water and matter cycles. Here just an overview of the industries applying the system, particularly breweries, food industries, but very especially also pulp and paper industry. And Jim Field, you heard him, you saw him, and you should hear him many, many times again. He did a very big job in this field. He was the second American who had a tremendous impact on my life. Positive, huh? Positive impact. And he was guided by Reyes. And she did the same in this field. So she supported him, she guided him, and she did the same with me. Together with Dora, of course. This is the first full-scale anaerobic reactor treating sugar-beet wastewater. Left. Left is the first one, and right is the demonstration scale reactor, 200 cubic meter. Has only been used for 1 year because it was proven. This is the biggest UASB reactor we have, I would say had, treating potato starch wastewater in the northern part of Holland. Very difficult type of wastewater. Just one difficulty I want to mention. This one was installed in 81. Campaign industry, only 2 months, tremendous big reactor, no seed sludge available, very difficult type of wastewater. So how to get things going? But what we found in the laboratory, the sludge, the anaerobic bacteria, they completely converted the pollutants into methane, but they didn't grow. We didn't have grow of new bacteria, which is essential. And only after we added a mixture of trace elements, the process, the bacteria started growing. So this is one of the very fascinating things of anaerobic treatment. Here a paper, reuse paper industry. The anaerobic reactor is here. This is the first one, the second one, because more and more paper is misused. Oh. And the old aerobic treatment systems are in the back. And the biogas is treated to remove the H2S. Then we have an expanded granular sludge bed reactor. It is using granular sludge. Can apply very, very high loading rates. They are very tall reactors. I just want to mention the work in the United States made in the 80s. Bill Jewell, Mike Switzenbaum. It's more or less exactly the same system. But we used the granular sludge, and they used inert carriers on which biofilm was developing. But expanded bed, not fluidized bed. And here you have these tall reactors. Initially, they were intended to be used as fluidized bed, complete fluidization, but was didn't work. Didn't work because we have detachment of the biofilm. So then later on, they started using the granular sludge. It was very successful. So, I just want to say something about the public sanitation sector. Very different story. I speak about the modern urban public sanitation sector. The collection is wrong. Concentrated domestic waste is flushed away with a lot of water. We have very big, expensive, vulnerable transport systems, the sewers. Non-sustainable. Every 40 years we have to rebuild them. We have these aerobic wastewater treatment systems which are energy demanding. And I hope I explained we don't need them if we do the proper job. It is going to be bigger, bigger, bigger. This is what you know, what I want to have eliminated. So we need a new paradigm in the public sector. This, I hope, clear for you. We need prevention of pollution of clean water. No misuse of tap water to flush away our concentrated waste. And we need valorization of the residues. And why? I already mentioned some reasons, but first of all, human waste, excreta and urine, and kitchen waste are extremely concentrated. We got it from nature. Human excreta contain major part of the risky organisms, the pathogens. So why to dilute this? Why should we create problems? We create problems. For waste valorization, we shouldn't have dilution. It makes things, everything more difficult. And the cost for environmental protections for the citizens should remain low. Just for illustration, urine contains 85% of this nitrogen. Feces only 11.5. So the black water, combined excreta and urine, 96.5%. Organic matter, mainly in the feces. Phosphorus in urine and feces. Potassium, especially in the urine. So I already presented this in the table, but you can see here the urine containing almost all the nitrogen. Here the organic matter, especially in the feces, in meal preparation. So if we combine these two, we have almost 70-80% of the organic matter. The P and the potassium. This is old-fashioned, may look old-fashioned, it is old-fashioned of course, but the idea, the principle is correct. Yeah? We keep the excreta extremely concentrated. They are collected, it has been used, I remember from my time when I was young, we used it in our farm. Yeah? Not merely this toilet, but there was another also. But it didn't stink. And down, it is going to be digested. Of course, we don't collect the biogas, but we don't pollute the environment. That is more important. So the new paradigm will lead, you understand what I mean, the correct collection, no water transport, the NBMS-based treatment, etc., etc. It will lead to a decentralized sanitation and resource recovery and reuse. DESER. That is what we promote, yeah? Or Ecosan. And Grietje Zeeman, she is also here somewhere. She is the big woman in our department working in this field and promoting this very, very much in Holland. And even from the established public sanitation sector, she gets more and more support. This research on wastewater treatment using the anaerobic wastewater treatment system already started in the United States in the 50s. Later in the 60s in South Africa, in 76 in the Netherlands, and around 2000 in Brazil. And the research has been directed to sewage and black and grey water treatment. Sewage treatment as a first step, and black and grey water. I want just to present, to my opinion, a very ideal solution for the public sector. It is just recently developed. We are going to introduce this with a group. The greenhouse village concept. It is a very holistic approach. We need a lot of different disciplines, sanitary, chemical, civil engineers, biotechnology, etc., etc., etc. Even lawyers, I think. And what is the idea? Very shortly. We have the greenhouse, and I just speak about Dutch conditions. We have the greenhouse for collection of heat during summertime, using a very sophisticated new type of heat exchanger. And the heat is collected using the groundwater, and the warm groundwater is reintroduced in the aquifer. This greenhouse also, it is a closed greenhouse, also produces food, crops, and clean water, condensed water. The aquifer we use for storage of warm and cool water. So warm water to heat the greenhouse during wintertime, and the houses of the community during wintertime. and in summertime the reverse. And we combine, that is the idea, we combine the system with the NBMS-based wastewater treatment system. So we have a community, minimum 200 houses, compartment building or whatsoever, and the wastewater from that community is treated anaerobically, producing energy. The biogas is converted in electricity, and the CO2 from that is reintroduced in the greenhouse because we need CO2 for breeding the plants. This is the concept. It is relatively high-tech, but if we use high-tech in the proper way, so for common interest, I think there is no objection against high-tech. It is not super high-tech. And in the public sector, we only can introduce these sustainable concepts step by step because we made huge investments in the centralized systems and in a sewer system, etc. So step by step, and the major first step in making modern public sanitation sustainable and economical is substitution of a conventional aerobic wastewater treatment systems by high-rate anaerobic treatment system. And the reasons for that I already mentioned several times: lower space requirements, saving energy requirements, etc., etc. So I don't want to go in detail. Here we have the sewage treatment plant Amsterdam with aerobic, with sludge digesters, with all kinds of settlers, primary, secondary. But if we replace the primary settlers and the aeration system and part of the post-settlers by one anaerobic pre-treatment step, so we save a lot of space, even in our moderate climates, but especially in developed countries. And here we have a pilot plant, which has been installed in 1983 in Cali, Colombia, in order to demonstrate the feasibility of the system for domestic sewage treatment. And based on the results in Brazil, very big progress has been made with the implementation. Here, Piracicaba. These three ladies were involved at that time in operating the plant. So, anaerobic pre-treatment, downtown, no nuisance, no odor nuisance in the treatment plants, and post-treatment in a kind of a lagoon. Colombia, the same story. We have anaerobic treatment under constructions here in the foreground, and sewage post-treatment, effluent post-treatment in lagoon. I just want to say something about renewable energy production from biomass. So what about that? It can be gaseous energy carriers for power supply of the citizens. Yeah? Methane, for example. Solid energy carriers for power supply of the citizens. But also liquid energy carriers, which has the big interest presently. And anaerobic digestion processes comprise, to our idea, a superior system for producing renewable energy from wet types of biomass. I am going to show you this. Just focusing on sugarcane, so Brazil. Of course, everything presently in Holland, in Europe, United States, wherever, so they want to produce alcohol, just for the car. So, considering what is going on, only the net energy production based on the energy content of the sugarcane is 38%. The effluent of the fermentation process contains about 10% of the net energy, but it is used in the fields for irrigation. So the energy present in the organic pollutants is lost. And half of the bagasse is also lost because the other half you need for distillation. We can use the anaerobic treatment system Then we have a net energy production of 48%, including 10% of biogas produced from the wastewater. We still have 25% biogas left. But it would be much better for many citizens to apply methane production, anaerobic digestion, directly to the juice. Because then we have 48% net energy production, we have 50% of the bagasse energy left, and we have all the nutrients left for irrigation. Or if we crush the stalks, the sugarcane stalks, and we apply direct anaerobic digestion, we have 60% net energy production and a lot of compost. So it's much more sustainable. I don't want to speak about that anymore. This is what is our fate, also in Europe. In Brazil we have these monocultures of sugarcane. This has to be in bigger and bigger, bigger areas. It is not biodiversity, I think. It's the contrary. The politicians in Europe and also oil companies, they want to force us in the same direction. We don't have the land. We are destroying our landscape just for making liquid fuel. And that is what I said. And it is written down here, and I'll leave it with that. And I come to my summary and conclusion. I hope I made clear that anaerobic degradation, we need it. It is natural, and it leads to new creative life for everybody. We should use anaerobic degradation processes. It is the crowbar to build sustainable environmental protection and production of renewable energy. And along with the development and implementation of sustainable environmental protection, we make progress to, that is what I hope, that is what I want, and that is what I expect, a more sustainable society. And a sustainable society, it is development of human resources. It is a robust supply of primary needs to all citizens. All citizens. It is conservation of natural and mineral resources. And we have a lot of tools. Just a few here. And I am not going to explain this or to go in detail because it is a matter of discussion. So we want to go, I think all of us, towards a more sustainable, more sustainability in a globalizing world. To my opinion, there are two main criteria for sustainability. First of all, it is resource conservation, fossil energy and chemicals, and diversity, biodiversity in nature. Secondly, maybe even more important, the well-being of mankind. Social security, work for everybody. Also, they should take the work. Spiritual development. And the priorities to be put, the first priority is for terrains fully belonging to our own human responsibility. Our own human responsibility. And the second, for terrains not or partially belonging to our human responsibility. So, what are we doing? An excessive use of fossil fuel. That is what we do. And it belongs to absolutely to our responsibility. We create a lot of CO2. Everybody speaks about it. It is may result in climate change. So, actions, prevention, problem prevention, first of all, and resolving or evolving problems inherited or self-created. So degradation to build social sustainability. I believe in smooth degradation, I think we have a good tool, crowbar, to create it. And so you may guess, we have light for the future, it is going to be night, or it is going to be a period of light or night. Thank you. I hope the first. Thank you.